For those at home, it's me again
I'll
still.
move you.
Excellent. Thank you for coming along to Bath Astronomers. Hey, this is a first, right? We have more people in the museum than we do online. Okay, we drastically reduced the amount of people online. I don't know what I've done with them all. We normally have about 10 or so, maybe 15 or so online, but we've got 4, but it's great to have you. So tonight, it's our May. Gosh, the year has whizzed on, and I'm glad to welcome our emergency speaker. And it's great that Bernard is able to be here, Bernard Henin. So we were expecting Pete Williamson. He sends his apologies, but life has dealt him a sort of a bad set of cards, bad hand of cards. So he promises to come back. In fact, we've booked him for, because we actually booked all the way through to the end of the year, we've booked him for March 2023. Okay, so you're going to have to wait just less than a year and see Pete's chat, but that's great. And Bernard is going to talk to us about other worlds with the JST. So what I'm going to do is just do some intro slides. So Bernard, overly keen there, you can sit back down again.
Oh, okay.
So we have our usual sort of welcome slide, but darkness is gone. I related this earlier on, that we're now in perpetual twilight for 2 months. It doesn't get officially dark from the end of May through towards the end of July. So we are now to a point where if you look to the northern hemisphere, you'll see the glow of the sun over the northern hemisphere, even when the sun has gone down midnight or whatever. So we're in perpetual astronomical twilight, even at the deepest, darkest moment of the night. It doesn't stop astronomy, but it means that if you like your faint fuzzies, you're going to have a hard time seeing a lot of them. Now, if you go quite low down to the south, there's still lots to see in Virgo, so there's some faint fuzzies to see there, but the further you get around towards the sun, the harder it is, because you just haven't got the contrast in there. But we're still doing loads of astronomy. Hey, and if the sun's out, why not do solar? So we're doing lots of solar stuff. So just either join in one of our solar events. I think we're going to have one on Saturday, so there'll be more on the Facebook group, but I'll also send an email about that. And we'll do more of that. And we've got regular stargazing sessions on as well. We're still at 84 members. So we were 84 last time, we're 84 this time. So we have no new members. So that's disappointing. So please tell your friends. Please get Granny to join, or Grandad, or anyone else. Great to hit a ton. You never know, it could be possible. So here's our committee. So if you see any of those in the street, then hide. They might ask you to volunteer for outreach or similar. But Camilla she's just actually had a trip out to the States with her school, where she was running a Lego kind of robotics competition, or her team, she was helping run the team in this robotics competition. I think it was in Houston. So she's basically been offline for about 6 weeks, organizing it all and doing it and now recovering. So, but she's helping us with, because she's a teacher over at Hayward Prep School. She's helping us not only as a member and an observer, but also to think about what we can do, rather than just pile into schools and say, here's a telescope, which is interesting, perhaps give a better offering. Sort of a bit more tailored that teachers can pick up more easily, and perhaps something that we can actually sort of deliver to them. They can have for a week, so sort of packs, and then they can go to another school, whatever. So we don't have to be there all the time, which means that we can sort of spread our coverage can be better. So that's what she'll be concentrating on. Chris, last month we heard that he was waiting for a shed. We don't know if the shed has been delivered. As soon as we hear the shed has been delivered, I'll let them know, everyone know that his shed has been delivered. Jonathan's off sunning himself somewhere, but he's been quite active on the outreach side. We did have Mike on a little bit earlier. He's currently in Barbados, and he's got telescopes out there, and he's constantly tinkering them. He's our basically in-house engineer. He helped us mend the Moncton Coombe telescope, so did Chris, but Mike's the one with all the grinding machines and all, he can make new parts. So he's been busy trying to automate all these telescopes over in Barbados. Lots of funny stories. I should leave him to tell them, but one of them involved popping a door open with a full diving compressed air cylinder in the middle of the night, and the door slammed and the cylinder went bang, bang, bang down the concrete outside his house. It didn't explode. Yeah, but that would have made a great astronomical story, wouldn't it? Whilst you were observing, you almost blew up the neighbour's house. Prim is a wonderfully keen, reasonably new into actually being part of the active astronomy crowd, but sort of a lifelong spacey, and definitely instrumental in helping us sort of organise with the university to access to the planetarium, and also doing loads of outreach for us as well. So great. And I don't know who the bloke at the end is, so let's just ignore him. So what have we actually been up to? Okay, running a planetarium isn't as easy as we thought. These are exactly the same photos as last time, because we're pretty much at the same point as last time. What we have discovered is that I'm an idiot, as my wife explained to me the other night when I told her all about these. So we've had problems getting the image on the inside of the planetarium to line up correctly. And I did loads of maths to work out all the light paths. And I was explaining to my wife, and she said, wouldn't you just move the projector closer to the wall? And that is the answer. But she didn't do any of the maths. It's unfair. So we've had 2 goes. And I think the third go, we might get it sorted with the third go. But it's actually, the dates are in the diary for this over the summer to run. This is part of the Herschel 200 activities. Get all kinds of children in here to watch sort of shows that we're going to build ourselves using Stellarium, but also using footage from ESA of things like the James Webb Space Telescope launch, so they can see the rocket going up. Bringing that all together, but knitting it into the William Herschel, Caroline Herschel, Alexander Herschel story as well. So they can come in and do that.
How many people get in it when it's up? How big is it?
It's quite spacious.
About 20 without them bashing in, 20 children without them bashing in, yeah. Primary school, sort of top of primary school. So
And then you're in there as well. So you've got to be...
you're in there as well, yeah.
It's quite big, it's not as small as you'd think.
So
I thought we wanted to start using it in half term, just like next week.
I thought it was, okay, well, then I am going to panic. I'm going to read an email and sort things out. Okay, right, but more importantly, we've been doing this kind of thing. So we've been doing outreach, so getting the solar telescopes out in the nice scenic part of Bath in front of the Royal Crescent there. People have been observing what's been a plethora of sunspots that we've had over the last few weeks and months. In fact, one of the things the metrics for measuring how busy the sun is, they have days without spots, and you have the number of consecutive days without spots. And I think last year there was there was a 69, I think it's about 60. I'm kind of guessing at the number, but it was about 60 days where there were no sunspots on the sun last year. This year there hasn't been, it's 0. Okay, there's been a sunspot on the sun at all times. Oh, that's great, thank you very much. So we're doing loads of that, and we're planning to come and do that again on Saturday. The Sky at Night program is interested, and they're potentially going to jump in a car for our next session, which is currently scheduled to be Saturday. So I'm really after any people that are interested in just popping along to help out and just guide. We've got a problem with a few people being on holiday, but if you do have the time and you do want to sort of come along, I can get you a little prep material to read up beforehand. And it's just like the Museum of the Moon. If you know a little bit more than the person looking, then you can give really good guidance. Okay, I'll send you the prep material. I better write it. Good evening.
Hello. Hi, good evening.
Okay, so I did remind that we actually, it's these 2 N telescopes on here. These are the best to pick up, the ETX90, and I'm trying to remember what this is, Celestron 114, I can't remember, LCM. They're go-to telescopes, just plug them in, make sure the batteries are in them, fire them up, they'll find, they'll tell you what to do, find star 1, find star 2, and then you can be observing. Those are there for loan. So we had one inquiry, but hey, it hasn't moved forward because, but hey, they're there for you. So please shout. So drop us a line. Yeah.
I'd love to. Yeah, I'll drop you a line.
Yeah, drop us a line and we'll do it. And for however you look, it's typically sort of we review at the end of the month. So, but people after about 3 months, they say, oh, it's about time to give it back. Yeah. But anywhere between 1 month and 3 months. Yeah. Okay, so what we do for actual stargazing, again suggesting some windows. So this coming weekend, if I don't fall asleep at Monkton Combe, the following weekend maybe Wello. That's slightly problematic. The reason is I think I've just promised to do 2 stargazing sessions for Bath Abbey on the 3rd and 4th of June on top of the Abbey, and the only star we're going to be looking at is our sun. So we'll be doing solar from the top of the Abbey, but we'll also be doing the moon as well. So it might actually be the 5th. I put the 3rd to the 5th there, but it might actually just be the 5th for Wello, but it depends how those go. Again, Moncton, and then why would I go for White Sheet Hill the end of June? That's because we're in noctilucent cloud season. It kicks off around about now, and this is where about an hour to an hour and a half after sunset, or an hour and a half before sunrise, if you look to the northern horizon, so just after sunset, it's to the northwest, just before sunset, it's to the northeast, but actually throughout the night, you can actually see potentially a band, and you know it's not ordinary cloud because it's bright electric blue. And you start seeing ripples through it. It's not actually moving, it's the way that the sun is projecting through these crystals that are about 70, 80 kilometers high. Noctilucent clouds. Yeah, and you see these electric blue clouds that hang over the northern horizon. In a good season, you'll probably get 3 or 4, maybe even 5 or 6 good showings of noctilucent clouds, but that's over a 3-month window. So you've got to sort of, you go out, look out an hour and a half after sunset. If there's nothing, then pop back in again. But it's one of those ones where if you're doing observing and you think, oh, I'm a bit tired, it's sort of like 2 hours till dawn. If you're that kind of mad, crazy, give it another half an hour. And the reason is because you might get noctilucent clouds. And that's exactly what happened at White Sheet Hill a few years ago. We were watching the comet Neowise, and one of us noted there's something happening over on the northern horizon, and a few of us were thinking about packing it in, but we didn't, and we got one of the most spectacular noctilucent clouds with a comet right in there too. It was like, even people with rubbish cameras got good photos.
Oh, wow.
Yeah, so sometimes it's worth just someone keeping an eye out for things like that. But yeah, it's a vivid electric blue, and it's really weird. It's the weirdest clouds. Actually, I've now seen some really weird clouds on the internet. So it's almost the weirdest clouds that you could possibly see. Next month, we're going to be blessed if she gets back in touch. I actually said she was the May speaker. Megan is down for our June speaker. I haven't managed to get through to her yet, but fingers crossed, I will get in contact over the next few weeks to make sure that she can give us a talk over Zoom. So I look forward to that. But our rescuer, our knight in shining armor, Bernard has come along here. I met Bernard actually on a radio show called Reach Out and Touch Space, which is unfortunately no longer with us, that particular radio program, but it's lucky because it introduces me to great people like Bernard. Now, Bernard is not a professional astronomer. He's a man who's very interested in astronomy and associated with astronomical societies and done lots of work and things like that. But he's the kind of curious person who realizes that when he's listening to or reading newspapers or listening to people being sort of talking about the solar system and things like that, that perhaps they're talking a lot of tosh, or there's sort of misconceptions or myths that they're just repeating. And there doesn't seem to be a definitive work on sort of the ocean worlds of the solar system. So Bernard is the kind of person who says, actually, I'm going to sort this out. And he goes and writes a book on it. Okay, so I believe this is sort of essentially quoted as one of the best books, if not the best book on ocean. You would agree that it's the best book on ocean.
I'm shaking my head there, yes.
So Bernard's got an interesting history and career, sort of traveled the world and things. So he's got that insight, but he's still got his roots and is still with this sort of linked up to some of the first astro organizations he's touched base with, such as the Sherwood Observatory as well. He's now based in Wiltshire, so he's actually a local.
I am.
Yeah.
Yeah.
And he's recently spoken, is it Marlborough College?
Yes.
Yeah. And he's sort of widening his scope for public speaking and things. So it was great that Bernard is able to join us tonight and talk about other worlds and the James Webb Space Telescope. So if you give him a little round of applause, I'm going to organise the slides.
Thank you, Simon. Yeah, I'm just going to start by saying it's a real honor for me to have been invited here, but especially to do a talk at the William Herschel Museum. This is such a special place. I remember I came here many years ago with my wife, and you know, just looking at, you know, in the garden where Uranus was discovered, it's just amazing. And for me to be able to be here and actually to talk about two amazing topics, the James Webb Space Telescope and exoplanets. And I consider Uranus to be an exoplanet in the metaphorical point of view, because before William Herschel discovered Uranus, no one knew there were other planets, right? There were only the 5 classical planets. And then suddenly he spotted something new, and sort of like, you know, you can sort of push the metaphor to a point where you can actually say that he actually discovered an exoplanet in such a way. But yeah, so as Simon said, so I actually studied biotechnology at the University of Nottingham. I'm not from England. I'm from Belgium. My first language is French. Nevertheless, I just went through I call this a sample career. I just decided wanted to follow some of my aspirations, and I worked for various companies. I worked for Amazon.com. I was a humanitarian photographer in Africa for a while, but I always wanted to follow my passions, and one of my passions has always been space. And I was very fortunate and lucky to be able to get in touch with a publisher, Springer, the biggest academic publisher in the world. And through various conversations, they were actually quite keen for me to start writing books for them. And the idea is that, yes, there are lots of, you know, as Simon said, there's lots of information out there, and sometimes this information might be misinterpreted or exaggerated. And they need people who can actually, you know, tackle a complex topic and actually manage to distill this information and republish it out to the outside. So that's what I do. I do that for Springer. Oh, how does this work? Is it?
It's the top one.
Is the top one.
Oh, that's actually
This is the Bath Society's ones.
Yeah, okay. Yeah. So just touch that, and let's just kick it back on again.
That's fine. That's fine. I just blame you.
Yeah, I am responsible. Hopefully that's it. And then the down button.
Oh, there we go. There we go. Thank you so much. Thanks, Simon. Yeah. So you can go and visit my website. So I published 2 books. So as I was saying earlier, so The Ocean Worlds of Our Solar System is a book about all the planetary bodies that have liquid waters, oceans of liquid water inside them. And there are 5 confirmed planetary bodies. And I talk about their habitability. And I reached out to lots of experts at NASA, a European Space Agency, to write this book. It had great reviews. And my latest book, which was published a few months ago in February, which had a fantastic review at the BBC Sky at Night magazine, which is talks about all the imaging. Oh, there's some people on Sky. All the imaging instruments that were sent into space, into all the spacecraft. You know, I go through 134 missions that went to explore the solar system, and I talk about the most important pictures that were taken, how they were taken, why they were taken, and the evolution of all these imaging systems from the beginning of the space exploration up until now. But today we're going to be talking about something really extraordinary, and this thing is not working again. Simon, help me, please.
I'll tell you what, we'll do next slide, please.
Okay, next slide. Okay, I'm going to talk about something really great, because there's a convergence of 2 amazing things that is happening at the moment in astronomy. The first one, of course, is the James Webb Space Telescope. And I know that you've had a talk recently in January about the James Webb Space Telescope. So I'm not going to go too much into detail on this. And we sort of already know anyway, this telescope. But the arrival of this telescope and the discovery of exoplanets is a marriage that is really, you know, it's a perfect marriage. And why is this talk I'm going to give to you so extraordinary is that this is going to start happening, kicking in the coming month. I'm going to show you some simulations and ideas of what James Webb Space Telescope is going to do with regard to exoplanets is going to happen now. They're going to start in the coming weeks. And that, for me, is just extraordinary. So next slide. So we all know that JWST is the biggest space telescope out there, 6.5 meters in diameter. Next slide. Yeah, but I'm going to ask you to. Well, I'm going to really present two key characteristics of JWST that's going to be very important for exoplanets.
Can you just press the bottom one?
That one. Very important for exoplanets. And I'm not going to tell them now because I want you to still be attentive to this talk. But as we're going to go through the talk, I'm going to really go a bit more into detail on these two key characteristics. Oh, Simon, I'm sorry, it's not working. Oh, there we go. It's back again.
Yeah.
So we're not going to go into this. I just wanted to show again, and we all know how big 6.5 meters is. But I mean, look at this image and look at this chap there at the top left there. I mean, this is just huge. You know, sometimes you need these type of images just to remind yourself what an amazing engineering feat it is to have, you know, send this thing into space, and like a transformer, right? You know, where you had to unpackage itself and unfold. It's just fantastic. Actually, by the way, who watched the launch live on Christmas Day?
Yeah, stop Christmas lunch.
Yeah.
The best Christmas gift ever, right? Oh, absolutely. Right. So I'm going to go back to JWST, but first I'd like to talk about exoplanets. So what is an exoplanet? We all sort of know what it is. It's a planet that orbits another star. That's not entirely true. Why is that? Why is that not entirely true? Because there are exoplanets, which we don't really know how to call them at the moment, planets that actually are out there in interstellar space that don't orbit stars, right? And we know that in the past of our solar system, there was another planet the size of Uranus, Neptune, that was ejected quite early on when the solar system was sort of, you know, going through its beginning phases, and that exoplanet is just gone, and where it is we don't know, but we know there must be a lot of these sort of planets out there. They're just not being illuminated by a star, so we just don't know how many there are, and it's going to be really difficult for us to find them. But at the moment, you know, this can also be classified as an exoplanet as stuff, right? Right. First exoplanet was discovered in 1992. Do you remember what type of star was it going around? No, it's actually no. Yeah, absolutely. It was discovered around a pulsar. Actually, there were two planets that were discovered around a pulsar. But we're talking about 1992. That's 30 years ago. We've been doing exoplanets for 30 years. And just for me, when I was doing this presentation, I was like, oh my gosh, it's been quite a long time, and it's great. However, you know, we know what's going on. Oh no! You know what? I'm just going to give that to you. So we know that pulsars, neutron stars, next slide please, is obviously not the best place to find a planet, because what of course is a neutron star? Pulsar is the remnants of, I'm waiting for the slide to come on. As well. Oh no, I have a clicker. Should I get mine?
Well, I know what you've done wrong, and I know what I've done wrong.
Okay.
And that's we're clicking that with the bottom one.
Yes.
We do the up and down. When you click the bottom one, it causes the confusion.
Oh, okay.
Yeah.
That's probably me then.
Yeah. Okay.
Right. Let me do this. Yes, it's working. Thank you, Simon.
Don't touch the actual bottom.
Okay. Okay.
Right.
Oh yes. Okay. Fine.
Right,
Yes. So there we go. So the first exoplanet was discovered around the remnants of such a huge explosion, right? So obviously, it's probably not the best place to find life if we're actually looking for exoplanets, maybe life. So when do you think the first exoplanet was found orbiting a normal star, an Earth, a sun-like star? Do you remember? Does that ring a bell, Simon? So it's... Okay, it was discovered in. You know what? I'm just gonna be there. It's still not happening. I press this one.
Yeah, that bottom one. Yeah. Sorry. The other thing that can happen is if I haven't clicked on the screen. So try it now. That's it.
There we go. Discovered in 3 years later, right? Orbiting. It was a 51 Pegasi orbiting a star, a sun-like star. We've called it Dimidium. Now the peculiarity of this star, of this planet, sorry, is that it orbits its star. It takes 4 days to orbit the star, and it's half the size of Jupiter. So we call this a hot Jupiter, right? You might have heard of this before. So what is a hot Jupiter? You take a planet the size of Jupiter, and you actually shove it right next to the star. And 4 days to orbit the star is incredible. How long does it take for Mercury to go around the sun? Do you remember? I'm putting you guys on the spot here, am I?
Is it about 2 months?
Yeah, 80 days.
Yeah.
80 days,
Yeah.
right? And Mercury, is the closest planet to our star. And here we have Jupiter-sized planets right next to the star. So anyway, what does it show us? It just showed us that exoplanets were incredibly varied and very diverse. So how do we detect exoplanets? I know you also had a speaker last year who came to talk about tests. I'm going to talk to you about very quickly 4 different methods to detect exoplanets. We have the transit method, microlensing, the wobble method, and direct observation. The 2 that are really going to interest us for JWST is going to be the transit method and direct observation. But I'm going to quickly go through them. The transit method, very easy to understand. If we're fortunate enough to be aligned with a star and an exosolar system where the planets transit in front of the star, where we're actually going to be able to detect those planets just by looking at the brightness of the star. We all sort of know this. This is what TESS has been doing, what Kepler's been doing, and has been returning fantastic and amazing science. I'm going to come back to this because JWST is going to be using this in an amazing way. The next method of detecting exoplanets is related to this. Do we know what this is? Come on, Bath astronomy. An Einstein ring. Do you know what an Einstein ring is? Yeah, gravitational lensing. That's when Einstein his theories predicted that if you have a huge mass in space and you have an object behind that mass, then this mass would actually be able to bend the light in a way that it would actually magnify the object behind it, right? Now, if you take this idea, this concept, and here we're talking about galaxies. In this picture you have, so the galaxy in the back is sort of distorted in this sort of elliptic shape by the galaxy in front, and we're talking about billions of sun masses that are being distorted here. But it allows us to really understand what's hiding behind this mass and actually be able to magnify the objects which is further away and maybe a bit fainter. We can use this principle and actually detect exoplanets, but it's counterintuitive, and I'll show you why. We call this microlensing, and basically what happens is that we have to wait for a star to be perfectly aligned with another star in the background, sorry. And we have to wait for a star to actually pass in front of the other star to be able to detect an exoplanet. And I have a cool graph here I'll show you now. So you see here, you have this star in the foreground with this planet in the foreground. And as this star is passing in front of the star in the background, it's actually magnifying the brightness of the star in the background. And what we're trying to detect is just the next dip here, where you see the light of the star in the background being magnified by the planet because of microlensing. So we're not trying to detect a planet in the star in the background. We're actually trying to detect a planet in the star in the foreground, which is very counterintuitive of how you actually use gravitational lensing. So there's one major disadvantage of this technique. Would you guys try to think of what would that be?
You have to be really lucky.
Yeah, and it only happens once.
Yeah.
Because once it's passed, it's passed. It's never going to happen again, right? And that's a big problem in science, repeatability of measurements and data. But it does happen, and we do find planets with this. And maybe, JWST might be lucky. I'm not quite sure, but that's not its mission. Another method is just called the wobble method, or radial velocity. And this one is quite easy to understand. As you have a planet orbiting a star, it actually makes the star move somewhat a little bit. The star is not fixed on a point, it sort of is being pulled by the gravitational pull from the planet. No matter how big the star is, no matter how small the planet is, there is still going to be a slight effect. And we can measure that effect with the light spectrum. Do you mind trying to relaunch that again? Yeah. Thank you. We can measure that the planets just by looking at how the light spectrum is moving, shifting back and forth as we're observing that star. Cool. So so what is that light spectrum? I thank again Pink Floyd for giving me the rights to use this picture. This is a prism, of course, and the prism is going to break down a light into its constituents and into its wavelengths. So we have the visible spectrum, but we all know that the visible spectrum is part of the electromagnetic spectrum, which is, of course, all the energy waves that are going through the universe as we speak. Now, this is really key to understanding JWST and what it's going to be able to do. I'm going to go back to that method, but now I want to talk about the direct observation method, which is the one that's probably the most interesting for us. And this is the one where I always have to try and manage people's expectations, because of course JWST is an amazing piece of engineering. 6.5 meter wide telescope in space. Oh my God, it's going to be fantastic. Are we going to see planets like this? No, unfortunately not. We're not going to see planets like this. And I've done this talk to I remember, yeah, Marlborough College, and you could see these, secondary school kids, and they're like, what? They don't understand, because they're just bathed constantly into this, impression that we might be able to see, high resolution images of exoplanets, continents and maybe lakes and all that. They're just so far away. They're just so faint. This is not going to happen even with the JWST. I will show you a simulation later on about what we think an imaging, the proper imaging of an exoplanet will be. Okay. And the reason, of course, we all know why we can do this is because, first of all, this is an image. First of all, the light, the brightness of the light is just extreme. This is a picture that Hubble telescope took of a star, and you can see 1 AU here is the orbit of the Earth, 5 AU is the orbit of Jupiter. So the brightness of the star just completely overweighs everything else, and so we need to find tools to be able to sort of block that light of the star. And for this talk, I actually I found this slide, and I thought it was interesting, and I remade this calculation. What we're trying to do is as if we have this huge strobe light here on the right that's based in Edinburgh, and I've made the calculations, and we're here in Bath, and we're trying to find a firefly that's just on the rim of this huge torchlight that's just beaming full whack at Edinburgh, and we're here in Bath. That's what we're trying to do. That's the level of technology we're trying to do, by trying to observe exoplanets. So it's the engineering, again, is just amazing and fantastic. But we have been able to do so, of course, and these are all from ground-based telescopes. But we have been able to capture for quite some time now, quite a few many years, exoplanets around their solar systems. Of course, these exoplanets are huge, quite a few times the size of Jupiter, and they are quite far away from the star. We're talking here about, probably at the orbit of Uranus, orbit of Neptune here, and even further away. So, these are easy, sort of, relatively speaking, easy planets to take pictures of. We also managed to take, of course, a video, through time of exoplanets orbiting other stars. Now, the exoplanet is not blue. That's just an optical effect of the observation. But I just find this completely amazing. By the way, 51 Eridani b is one of the exoplanets that James Webb Space Telescope is going to actually look into this year. So we also can visualize exoplanet systems. So here we have 4 exoplanets going around the star. And it's just fascinating. Going back to what you said about the Fomalhaut system. Yes, it's a very famous system. Okay, we also can see early solar systems, right? When I do this talk for kids, I've done this type of talk for kids, and I call these baby solar systems, and they love that. But it's amazing because we actually can see the formation of the solar systems, of previous solar systems, and it's fantastic. So what have we found so far? Of course, we found that solar systems, other solar systems, are very different from ours, and there are lots of exoplanets. How many have we found so far? The figure came out in the news media last month.
They've just gone over 5,000.
Yes, 5,000. Yeah, 5,000. It's amazing, and it's all comes from all shapes and sizes. It's just phenomenal what we're discovering. Here's a chart that's trying to classify exoplanets. It's not too late of a chart. So this is the orbit around the star. So at the bottom, the x-axis, and the y-axis is its mass. And you can see that, you know, the transit method here, that's through Kepler and TESS, has been discovering a lot of planets that are quite massive, but actually quite close to this parent star. The imaging technique, of course, is here at the top right, is obviously, you know, at the moment, we're just limited by the technology. So we can only, you know, detect really heavy planets that are quite far away from their star. And we also have micro lensing and some radial velocity as well. JWST is really going to be doing lots of transits and lots of imaging. And we're going to go through this a bit more in detail. What have we found? We found that exoplanets really come in very different type of categories. We don't have any analogs here in our solar system, right? There's a lot of these worlds which are between the Earth size and Neptune size, sort of mini Neptunes and super Earth, that we just don't know what they really are. We really have no example of those in our solar system. There's one cool category here at the bottom left called lava worlds, and those are worlds that are terrestrial worlds, rocky worlds, but are so close to the parent star that they're most likely, you know, just incredibly infused with heat, and, you know, the surface is most likely melting. And of course, we've discovered some really cool solar systems. And we've all heard of the TRAPPIST-1 system because it's the discovery that showed us that there actually exists a solar system with 7 Earth-like rocky terrestrial planets orbiting a star. In this case, the star is a red dwarf. It's a really small star. It's going to be important later on in the talk because we're going to talk about TRAPPIST-1 system. But this is just amazing because we do think that some of these planets here in the TRAPPIST system are in the habitable zone, you know, that famous zone where, you know, liquid water might actually exist. And we've also discovered exoplanets in the solar system next to ours, in Alpha Centauri system, and closest stars, because of course there are 3 stars in the closest star system to us. The Alpha Centauri has two binary stars with a smaller star orbiting those 2 binary stars called Proxima Centauri, which is also a red dwarf. And around Proxima Centauri, we found 3 exoplanets. And amongst these exoplanets, Proxima Centauri B and C are considered to be in the habitable zone as well. So even the closest star system next to us, you know, there are potentially habitable environments there. Isn't it amazing? You know, just absolutely mind-boggling. And so here comes JWST, right? I've just given you this amazing and, you know, snapshot of you know, what is out there ready to be explored. And so I'm going to quickly go through JWST, and then I'm going to merge them both. And you'll see at the end of the talk, I'm going to do some simulations. So what are the 2 key characteristics? I'm going to give them, but not straight away. We all remember that JWST is now currently at Lagrange 2, 1.5 million kilometers away from us. Let's not forget that we already had observatories there before, right? Planck was there before, so it's not something new, right? We've been doing this for quite some time. Why is it in space? What's the point of sending an observatory into space? Because, of course, we have the atmospheric windows, or atmosphere blocks certain amounts of wavelength from the electromagnetic spectrum. And especially in this case, James Webb is going to be focusing on the infrared, and you can see in the atmospheric window here is sort of filtering a lot of this infrared. So why do we want to have JWST in space? It's because we cannot actually look at some of these wavelengths on Earth at the moment. So again, this is the electromagnetic spectrum at the top, and we've been sending quite a lot of assets into space. Most of them are really small. Okay, you might have probably heard of very few of them, but you're probably going to recognize a few names here. You have Spitzer, COBE, and if you zoom in, you have the HST, Hubble Space Telescope. And you can see here that Hubble Space Telescope is sort of capturing the visible light and the UV and some of the infrared. And then you have some of the others. Where is JWST going to sit on this? A lot of people say, and you read it on the news, on the media, and I hate it because they say it's the successor. JWST is the successor of the Hubble Space Telescope. It's not. It's absolutely not. If you look at the wavelength that JWST is going to look compared to Hubble, Hubble is really a jack of all trades, right? It looks into the UV light, it looks into the visible light, it looks into the infrared a little bit, right? It does a little bit of everything, and it produces amazing images. I'm not here to say that Hubble is actually not a great space telescope. It's the most amazing space telescope ever. But Webb is actually going to look at the infrared, the near infrared and mid infrared. So I think it's more a successor of Spitzer, for example, who was really a dedicated space observatory that was just dedicated to infrared. And that's what JWST is going to do. And you can see here that there are 4 different imaging systems. You don't need to look into this in too much detail, but you can see here, this is the wavelength again, and this is the red and then all the infrared wavelengths. And you can see that all these 4 different imaging systems are all built and designed to really study this infrared range. So why is JWST looking into infrared and mid-infrared? Right, let's remind ourselves, what's the main mission of JWST? Why do we launch JWST? I'm throwing this on the floor.
We had too much money, and so we built
Absolutely, to look back. We want to look at the early stages of the universe. So why is infrared important? Because again, let's go back to electromagnetic spectrum. And let's imagine that we have a star, one of the early stars in the universe that's emitting light, lots of visible light, as it's currently, going through its early stages. Unfortunately, something dramatic happens to our universe after this light is being emitted, and that's the Big Bang, not the Big Bang, but the expansion of the universe. The universe expands, and the expansion of the universe, of space, actually forces this light wave to expand with it. Sorry, that went a bit too fast. And because of the expansion of this light wave, what happens is that the light wave is actually going to shift from visible light to, sorry, I had something here, but I don't know why it disappeared. The light wave from the star is going to go from visible light to infrared as it's actually going to increase in length. Yeah, we all got that? And that's what we call redshift. And that's why this is one of the earliest galaxies found. That's why they're red, right? Because their light is being pushed into the red zone. This is a Hubble deep field, ultra deep field survey. It's one of these amazing pictures that Hubble took. It took 12 days to build. And you have, I think, 5,000 galaxies on this picture. And you see all the red galaxies they found, the faintest galaxies ever that we found in space at the moment. So JWST is going to do that. It's going to want to actually look even further in the infrared to try and find even earlier galaxies. I want to manage your expectation here. The picture that JWST is going to take are going to be very different from the ones that Hubble. Again, going back to the point that it's not a successor of Hubble. When you look at a galaxy through a visible light on the top left, it's amazing, it's wonderful. It's just, it makes us so fall in love with space. When you look at the image at the bottom left, that's a galaxy in infrared, the same. It's great, it's fantastic. Is it amazing? I don't know, but it's definitely a very different image. We're not going to see the same type of visual, amazement that we're going to see with pictures.
Use any false color?
Sorry?
They're going to use false color.
Yes, they're going to try and remake it so that it looks a bit better, of course. But from a scientific point of view, this is the data that they're going to want. There's another reason why JWST is focused on infrared. Why is that? Because it wants to look at objects that are really faint, but not galaxies or stars. Are going to look at planetary objects, such as dust clouds, or really faint objects, such as small planetary bodies. So why infrared? Because, as you probably all know from your physics lesson a long time ago, every object that is over 0 Kelvin, right, emits heat, emits radiation. And so JWST, what it's going to do is going to try and actually, it's basically going to measure heat. It's going to be measuring heat throughout space, and that heat, like you remember where I was talking initially at the talk from, there were rogue planets, planetary bodies that are outside into space that are not illuminated by a star, that are just very dark and faint. They're emitting heat, right? If not the light of a star, heat. And JWST or any telescope that's in the infrared will be able to pick up that heat. right? Here's a star, and you have an exoplanet next to it, and this is in infrared. These are the wavelengths of infrared, and you can see as they increase the wavelength, we're actually having a much better detection of this potential exoplanet. In this case, it seems like the exoplanet might not be as brightly illuminated by the star. I'm not quite sure why, but anyway. Again, manage your expectations, because what we see in visible light, what Hubble does, this is what JWST is going to do, is going to show us something amazing and different, but it's very different from the amazing images that Hubble has taken, right? Okay, so in order to be able to measure heat, what does JWST need to do? It needs to be very cold. And I don't know if you guys have been following this on your phones. Have you been looking at this since JWST was launched? Every day I've been looking at my phones, because here you have the thermometers set up all around JWST, and you can see these are the instruments, and you can see the temperature of these instruments going down week by week by week. And it's been amazing. And especially this is MIRI, the mid-infrared instrument. It's at 6 Kelvin. Let's remind ourselves that Kelvin is minus 273 degrees centigrade. And this MIRI has a cryocooler. So all the others are roughly around 39, 35 Kelvin. That's sort of the passive cooling system of being in space. But MIRI needs a cryocooler to actually work at extremely low temperatures in order so that those instruments are not going to interfere with the data. I was going to try and track heat, right? Does that make sense? So that's the first characteristics. James Webb is going to be looking at the infrared, okay? So I have a second characteristics, and that is talking about exactly the imaging system that James Webb has. We all know that most imaging systems are very much basically like framing cameras, right? We're just going to take a camera out in space. It's an amazing camera, of course, but it's still working like a framing camera, like the camera on your phone, okay? And JWST has these optical cameras, but it also has a spectrometer. You probably have heard of this before. What does a spectrometer do? It actually, again, breaks the light and gives us the light curve of an object, but through a spectrograph, such as this one. And basically what it does is that it just breaks down the light, and it allows us to actually identify elements and molecules that are being produced within the object that is emitting the light or reflecting the light. And this is very important. This is the second characteristics I wanted you to remember about JWST, is that it has amazing state-of-the-art spectrometers. And this is going to be very important for the study of exoplanets. So it's going to be very important for exoplanets. And I just wanted to show you here that within the spectroscopy range, within the optical range, the imaging range, we only have 3 instruments that are really going to be focusing on the optical imaging range, right? But spectroscopy is so important that we actually have 4 imaging instruments. Now they overlap because there's only 4 instruments, and they manage to sort of filter the light through one way or another. But that's why I really consider JWST to be an incredible asset for its spectroscopy. So let's do some simulations and look at what is JWST going to be able to do from an imaging or spectroscopy point of view, okay? So let's imagine that we have an Earth-like planet that's currently sitting at Proxima Centauri b. Remember the closest star system at us? What do we think JWST is going to be able to do from an imaging point of view? Not spectroscopy, but just take an image. It's going to do something like this. Probably like this, most likely outcome, just a pixel. If we're very lucky. If we're very lucky, it's going to produce a pixel of that exoplanet. So, you know, again, managing our expectations. There's a lot of information that can be gathered out of this dot, this pixel, okay? Let's not forget that, you know, if the Earth is imaged with this dot, that dot will change gray, will change color as we look at the Pacific Ocean, as we look at cloud formations, as we look at continents. So just looking at the variation of dots, just going to tell us that there's some variation in the surface of the planet, but not much else. And this is where spectroscopy comes into play. So if we're actually going to take the light of a star and we break it down as normal, as I've showed you through spectroscopy, we can do something really cool. And that's with the transit method. And you probably heard of this before. Basically, we actually wait until the planet transits in front of the star. And we actually are going to look at the light from the star as the planet goes in front of the star. And we're going to try and determine if there's an atmosphere. And if there's an atmosphere, we're going to try and pick up what elements from the atmosphere we can detect on the spectrograph. So basically, the atmosphere is going to filter through some of the lights of the star, and we're going to be able to detect sort of like a signature, right, of what that light, what the atmosphere of that planet is going to do, is going to be composed of. And it's called transit spectroscopy. We've been doing it for a long time. The first one was done in 2001 with a huge Jupiter-sized exoplanet. And the first element that was discovered was sodium. Okay, so we've been doing it for more than 20 years. So it's tested and it's been working quite well. And this is the power of James Webb Space Telescope. We're going to be combining the spectroscopy of JWST and the transit method to be able to characterize these atmospheres. Oh, there we go. So again, we're going to look at the electromagnetic spectrum. If you recall, I was showing you here at the bottom, you have the wavelength at the bottom. And basically, if you map out the spectroscopy of an atmosphere, a simulated atmosphere here, where you have different elements or gases such as methane, carbon monoxide, water, you will see, and I've sort of managed to try and map it out on the James Webb here instrument package here. I've sort of managed to map out, and you'll be able to see that actually the instruments are actually designed to be able to pick up those traces within the atmosphere. That makes sense? So if we have a spectra like that of an exoplanet, what can it tell us? Of course, if we have different types of concentrations of gas, such as oxygen and ozone and methane, and we have a combination of these gases, we all know what this might tell us. It might say, oh my gosh, there's life. And of course, this might be the first sign of life that we might find. And this is going to be on all the newspapers on the world. And people are going to say, what's this graph? What does this tell us? What does it mean? You know, what are these things? Is it aliens? What are they eating? How do they look like? We have no idea. We're probably not having any idea for a long time to come. But this is probably going to be the first sort of life detection as such. And JWST might be able to do this starting from next month. And I'm going to show you some simulations. Because this is the program cycle. You can all go visit this. This is the Space Telescope Science Institute based in Baltimore. And they are the organization that actually manages space telescopes, the Hubble Space Telescope, JWST, and the Nancy Gray very soon. And basically, you can actually go on their website and actually see at all the program cycles. What are they going to do this year for the first year? Program cycle 1 is the first year, and you can see that, you know, they're going to go through, they're going to do lots of things, protostars, galaxies and whatnot, but they're also going to look at extrasolar planets, right? So you can have a look, you can go really drill down onto this. You can see who's, you know, who's the PI, what instruments they're going to use, and then you can actually click on this hyperlink and you can go really in detail and dive deep into all these amazing programs that they're going to do. Again, some more program cycles for cycle 1. And again, they're going to look at exoplanet and disks. So JWST is going to be a workhorse when it comes to observing exoplanets. So I'm going back to TRAPPIST-1 system because this is the exoplanet system that's going to be the most studied by JWST in year 1. There's 5 or 6 programs that are going to be looking into this system, and the reason why is because, again, these are 7 Earth-like planets, sort of Earth-like size, and 3 of them are within the habitable zone, but we're going to study all of them. And JWST, so here we have all these 7 planets, and JWST is going to study 2 transits of planet B, 6 transits of planet C, 2 transits of planet D. You see the point. JWST is going to be looking at multiple transits of all these exosolar planets. of the TRAPPIST system, and it's going to do some eclipses as well. You might have not heard of eclipses. It's the opposite of a transit. Basically, when the exoplanet goes behind the star, we can also measure that, and we're actually going to be able to measure the day side face of the star, whereas a transit, we're measuring the night side of the star. And when a planet does an eclipse, we can actually sort of measure the temperature, the day temperature of what's on the surface of that star. And when it does a transit, we can measure the night temperature. And this information, day temperature, night temperature, gives us a lot of information about an exoplanet. However, I have to caution you, we currently have no idea whether any of these exoplanets have an atmosphere. We really don't. We just haven't had the capabilities to be able to measure that. And that's where JWST is going to come in. So whether I can't remember, was it DEF? I can't remember which one was habitable. But you know, if some of them have an atmosphere, if they have oxygen, if they have carbon dioxide, ozone, we're going to pick it up. And we're going to pick it up. It's going to start coming next month. So this is happening, guys. This is really happening. You know that chart I showed you about life? Maybe at the end of the year, this is what we might find and expect. One important thing, again, about JWST and in infrared is that these planets are orbiting a red dwarf. A red dwarf is a much smaller star than ours, the size of Jupiter, and red dwarf emits in infrared. So most of the light that these planets are being bathed are in infrared, and that's why JWST is really important, because most of the wavelengths, the information we're going to get from the electromagnetic spectrum are going to be in infrared. All right, hugely exciting stuff. I just can't wait. This is a simulation of what a spectrograph is going to look like. So you have a NIRIS, which is one of the instruments on JWST, and NIRSpec. And this is what it's going to look like. This is what we think might happen. If there's oxygen, if there's CO2, if there's ozone, these are the different graphs that scientists are going to be able to extract from the data and say, yes, this is what's happening around one of these TRAPPIST system exoplanets. So it's just fascinating stuff. Okay, so in the JWST's first 12 months, in regards to exoplanets only, there are going to be 95 programs. So 95, you might call it missions, that are going to be observing more than 100 exoplanets. 70 are guaranteed time, 25 are guaranteed time programs, and 70 are observation time. The GTO and the GEO, it's fine. You don't need to worry about it. It's just if something really goes wrong with JWST, the GTO is the priority, right? But we're going to have lots of observational time, 6,000 hours of observational time of JWST to look at exoplanets. And the first exoplanets are going to be imaged, and it's probably happening now, are these 5 planets, exoplanets. The reason why they're being imaged now is that it's part of the commissioning plan. They don't want to go and start these observational programs without sort of test drying, doing some dry runs in some exoplanets, just to you know, put some oil here and there and make sure that everything's running fine before we start the actual observations. And so these planets, for example, WASP 39b, 18b, and HIP at the bottom here, bottom left, these are all Jupiter-sized planets. And we're going to try and observe the atmosphere, trying to do some imaging. HD 141569a, that's more of a dust cloud around a star. So it's really just we're trying to do some dry runs before we actually go into this. And my understanding, and of course, I'm not part of the JWST team, but when you look at the information trickling down through, this is most likely happening now after the commissioning of the instrument. So we're going to be looking at exoplanets, guys, and it's happening now. So quick note on the future. Again, let's not forget that we have these huge Earth-based telescopes coming out. Especially the ELT and the TMT. ELT is going to be 39 meters wide. That's 6 times the size of JWST. They're of course going to look only in the visible range or whatever range they can look through the atmospheric spectrum, as I showed you. And of course, we have plans for bigger, better, more expensive space telescopes after the JWST. And the idea is to have a huge star shade to be able to block the light of the star, to be able to get a much better imaging of an exoplanet, because that's what we really want. We want to see an image of an exoplanet, right? You got to hold your horses there. It's probably not going to happen before 2050. Looking at how long it takes to find the budget, how long it takes to build these things. I'd rather be very conservative. Look at what happened to Jwst and how many years of delay it's taken, right? So this is not going to happen for quite some time. And even if it happens, the next generation space telescope that will have the optical capability of looking at a star system is still not going to be great. This is what we think it might be able to see when it's going to look at probably the closest star systems, just a few light years, maybe less than 10 light years away. This is what we think Earth might look like, Venus and Jupiter. So we're still not going to see continents and oceans and all these things, right? But we're going to have enough information here at least to start to make some guesses as what these planets look like. And even with just these blobs, we might be able to make out some continents. This is, for example, a simulation of what Earth might look like with these blobs, and you can sort of see that you might make you might have an idea whether there are continents and how big they are. All right, so the key takeaways from this talk, right? Lots of exoplanets, of course, amazing new frontier, ready for us to discover. Lots of exoplanets in the habitable zone, lots of Earth-like planets waiting to be discovered, such as the TRAPPIST system, which is going to be, probably the most studied exoplanet system in the coming year for JWST. And JWST, as a reminder, the two key characteristics I want you to really get in terms of the exoplanet study is the infrared and the spectrometer. All right, because at the end, this is what we want. We want to see whether we're going to be able to find life or not on these exoplanets. So there you go. That was my talk. I hope you enjoyed it. And yeah, the floor is open for any questions you might have. Thank you. Thank you.
So if you're online, feel free to open up your microphones. And what questions do we have for Bernard?
I've got one. So obviously that's great to see what the images might be of the exoplanets. But you mentioned that it's also going to look at the deep space objects back in time.
Yes.
And you showed the red.
Yes, the redshift.
What else could that? How far back could it genuinely go? Is it likely to find things we didn't expect to see, or?
Well, we hope we're going to find things we don't expect to see, right? We hope to have that surprise. But I think the last estimation was that it's probably going to be able to look back at 100 million years after the Big Bang. I'm not quite sure, in terms. Well, they're definitely going to try. The idea is to look at early galaxies. How do they look like? What type of stars, were being birthed within those galaxies. But in terms of the actual date, I don't have that in my head. Maybe someone else might have a better understanding. I think it's 100 million years after the Big Bang.
Which is considerably more than.
Yes, because Hubble was oh, actually, I do have a slide. Hold on a second, because I have lots of slides. If you just bear with me a second, what's going on? Is this? Oh, this click. Right. I have a slide. Hold on a second. I'm going to go through this. But I have a slide that shows. I think I'm going to do this. Do you mind 2 seconds? Yeah. Thank you. Oh, where is it? Oh no. Apologies for that. I thought I had the slide here on this presentation, but it's not on this presentation. So apologies for that. But yes. Check it out. Oh yeah, totally. Because it's the infrared. Yeah. We've never had such an equipment in space before. We've had infrared telescopes, right? Spitzer. But we've never had a telescope with such a high resolution focusing in infrared. And that's the key for us to really get by. And therefore, we're going to be able to look at the faintest objects ever, whether they're going to be galaxies or, stars, potentially even, right? Yes?
Do you know how they're physically going to point the scope?
Well, there are guidance systems that you...
physically going to move.
Yes. So there's so basically there's a fuel, right? There's a fuel that actually is going to target the telescope to the various targets it's going to go for. So it's going to move around. We think that there's enough fuel in there for 20 years. But of course, it's limited by the fact that it cannot look too close to the sun, right? So it's not going to be looking at any planets, for example, within the inner solar system. It's going to be able to look at Mars and further away, but not Venus, not Mercury, not even Earth. It's too close to the sun, right? So yes, the solar shield, it's fine. It can, it can move around, but you still have this constraint that the instruments need to be protected from the heat of the sun. But we have 20 years worth of lifetime on GWST, which is amazing. And that's again thanks to the amazing launch, from Ariane 5. They did like the best job possible to launch GWST at the best trajectory. Therefore, it used less fuel to actually reach the L2 point, and therefore there's more fuel for its lifetime. Yes, Prim.
Brilliant talk. I really enjoyed it.
Thank you.
I have a couple of questions. One was about the temperature. We were talking about it. So you said about these instruments and these really low temperatures. How are they being protected from the sun? From the heat of the sun?
Space shield, the sun shield.
Yeah.
So it's just that.
So it is that.
They're just behind. This is a tennis-sized court shield with 5 layers. And actually, if you look back, if you can actually go, there's something called Where's Webb, which I showed you a screenshot earlier. We can actually see the thermometer, the temperature on the James Webb, and you can see the temperature here is like at 50 degrees, 180 degrees, right, depending on where it is on the sun. And the temperatures here, as I showed you, was like 36 K and even lower. And the only reason it's so low is because you have this massive sun shield, right? That's exactly why it was designed for.
So not only does it have to make sure that that's always got the sun on its back, and it sort of also points at where it's pointing.
Exactly. So there are some constraints there. Absolutely, there are things that but Lagrange point is also great because it's going to travel with Earth as it orbits the sun, right?
Sure.
So it's going to be able to see most of space, right, at some point in time within the year, right? It's just always going to be constrained of not being able to see the inner solar system.
I had a second question.
No, go for it.
About the spectrometry, and that was so when it was really fascinating. It's going to look at these exoplanets and look at the atmosphere just as they transit in front of the sun, in front of the star. So what happens when you get 2 planets that maybe are both transiting in front of the star at the same time, and you get the light? You're
going to get a mixture, yes.
So you will be able to unravel all of that.
Maybe because, but it's a good question, and I don't know how they would unravel it. I would presume that those planets, there's going to be an element where they're probably not the fact that they're going to go behind or in front of the star at exactly the same time might be a bit I don't think. I think there's going to be maybe a few seconds before or after, and they're going to be able to pick that up. Again, these instruments are incredibly precise, incredibly minute, and the data processing is going to be incredibly hard and difficult to get, to pick out all the noise, to extract the meaningful information. We're talking about cutting edge technology. No one's ever done this before, and it's going to be a very, very, very painstaking work of months on end. So, I was telling you about these observations. It's going to happen now. You're probably going to hear about it maybe in 2-3 months from now. It's going to take months for these teams, with all their simulations and all that, to be able to extract any meaningful information. Any other questions?
So I'm fascinated by the thought of all these images. So there's been talk about the black hole at the center of the Milky Way.
Yes.
Shown. Again, are we likely to see that?
No, because that's the Event Horizon Telescope. That's very, very different. Very different. They're using multiple telescopes across the world to combine and create this amazing visualization of a black hole. But that takes months of observations, right? Combined months of observations with multiple telescopes around the world. That sort of mimics the idea of having a like kilometer-wide telescope.
What would JWST see if it looked at the same place? Would it just be seeing the stars around.
It will most likely see the stars around, but I don't think it will have enough resolution to be able to actually see that in too much detail. All right.
Are we expecting to see perhaps like Saturn's, any ring or?
Oh, absolutely.
Yeah.
Oh, what? In exoplanets,
Yeah,
you mean?
yeah. So
Yes, yes. So maybe not rings, but there's an idea that we might be able to pick up some moons, comets in the some dust clouds in the comet, in the rings, so there's. But again, we're not going to probably have an image of those. It's just going to be a graph, a chart, and there's going to be a speck, something going up and down. We're like, oh, look, this is potentially a comet or something like that. But we look, for example, when you look at some of the solar systems, I showed you a picture of the formation of the solar system. You can actually see these dust clouds, forming. Some of these images, you actually see an exoplanet. We're talking about a big one, right? The size of Jupiter. And potentially you might be able to see, and some astronomers claim that you actually might be even to see a moon starting to form on the side, the way the mass is actually starting to aggregate next to the other planets. So
you see new solar systems actually being formed.
yes.
Right.
Yes, and JWST is going to work a lot on that, actually. It's a good question because it's part of those observation programs. One of the missions of JWST is to understand the formation of solar systems. So it's actually going to observe a lot of them as well. It's going to revolutionize astronomy. Again, it's going to be fantastic. My passion is our own solar system. I write about it. I write about the missions that go and explore it. And what JWST is going to do with our own solar system is just, it's going to be able to start looking at Pluto again, and Triton, and the dwarf planets, and the moons and asteroids, and it's going to be fascinating. The information is going to return again, only in infrared, but still, it's going to be amazing. And one of the key things that we hope JWST is going to be able to do is, those interstellar comets or asteroids that came in, Oumuamua and Borislav. We hope JWST is going to be able, if possible, again, going back to the constraints of it has to be pointed in a certain direction at a certain time, and if possible, if one of those interstellar objects is going to come into our solar system and we're going to detect them, we hope to be able to use JWST to be able to start characterizing the surface of this object, and that's going to be phenomenal as well. Because one of the power of JWST over an Earth-based telescope is, of course, an Earth-based telescope, the Earth is moving. And at some point, night becomes day. Whereas JWST, even though there are some constraints in how it can be operated, it can actually have longer observation times. We're talking about many, many hours, maybe 10, 15, 12 hours in continuum. And that can extract a lot of information from us. So JWST is going to change our understanding and return so much information. It's mind-boggling. If you go and look at all the available data out there from this space instrument, Space Science Institute, they're based in Baltimore, and you look at all the observation program that JWST is going to do on the first year, it's just mind-boggling. The amount of data is going to return, and that's just 1 year. And we're expecting it to work for 20 years. So this is going to be an amazing thing. And especially in this case on exoplanets. So I'm expecting coming within 6 months from now, we're going to start to see news, and lots of news of discoveries of formation of, planets and exoplanet atmospheres and this and the earliest galaxies, and it's going to be drowning us with we're going to have a great time. Yeah, go for it.
I was thinking it was going to be looking into deep space, and it's very interesting you say it's going to tell us a lot about our own solar system.
Yes.
I just wondered whether it's going to be able to capture anything at the sort of outer reaches of our solar system, stuff that we don't know about, that's still a mystery to us.
Absolutely.
Or is that too cold?
No. Nothing's too cold for JWST. everything's hot for GWCS. So, you saw
Yeah.
6
Yes,
Kelvin,
yeah,
right?
6 Kelvin, yeah.
So it's going to pick up everything. So basically, you've all heard of the hypothetical planet 9, right? This potential planet that's lurking out probably 100 AUs from here. If we actually starting to have some, some confirmation of this planet 9, JWST is perfectly designed to see it because it's going to be infrared. That planet is so far away. It's going to be really dark. It's going to be very cold, very poorly illuminated by the sun. We need something in space that's going to be able to capture it, and JWST is going to be doing it. So, no, it's Christmas. It really is. It really is.
Is it robust enough? Is it in any danger from space debris? It looks quite delicate.
No, it's really an interstellar space. Not interstellar space, but I mean it's interplanetary space. So there's not much going on. If it had to go near the asteroid belt or the rings of Jupiter, of course, the rings of Saturn is going to be a problem. But there's yes.
If there was a planet 9, wouldn't we have already discovered it? Because we've already seen things that are much further away than the edge of our solar system. So wouldn't we have already been able to discover that?
No, because we still don't know where it is, if it is. We have ideas about. There are simulations that have been running about where it could be detected. But we haven't actually observed it yet. So, but space is big, so we're not going to. There are no plans, unfortunately, for JWST to start spending 3 months looking into the entire space to look for Planet 9. That's just not going to happen. So we're going to wait until another Earth-based observation is going to be able to spot it, and then we'll target JWST on it.
So JWST is essentially a follow-up telescope. It's going to give the detail. That something's going to have to spot it first, because it's too important to be spending lots of hours searching.
Absolutely. We're talking about hundreds of teams of astronomers around the world that are trying to use JWST. So and there are far more important targets at the moment. Enceladus, Europa, the plumes of Europa, the plumes of Enceladus, these ocean worlds. Titan is going to look at Titan with infrared. So Titan again is the biggest moon of Saturn, enveloped in this atmosphere, right? This very thick atmosphere. Infrared manages to go through this atmosphere. We're going to be able to look at layers of Titan through Titans. Cassini did that actually through its infrared cameras, right? Looked at different layers. And JWST is going to be able to do that at resolutions completely unheard of, at least unless you send a spacecraft there, right?
Will that be better than Cassini?
No, because Cassini, there's just the fact of just being there, right? Yeah. 300 kilometers above the surface, But no, we're going to be able to see, seasons maybe on Titan, as we're going to do these observations. So what it's going to do for our own solar system is going to be transformative, absolutely transformative.
A number of scientists have basically wrecked their careers by saying there's life on Venus, there's life on Mars.
Yes,
so
yes.
Do you not think that perhaps that people are going to be, or some scientists are going to be a bit cautious, even if they do find some of these processes?
Absolutely. Yeah. Phosphine is starting to bite some of these Venus scientists now. Absolutely, and especially because there's a lot of processing that goes into this data, and there's a lot of simulations. At the moment, lots of scientists have been doing simulations. If there is some life, Earth-based life form, what would it look like on these TRAPPIST systems? And so they're gonna have sort of this template, this example. We think it's going to look like this. There's a lot of uncertainties and lots of factors that go into simulating these type of things and into extract the data and interpret the data. Thankfully, what's going to happen is that you're going to have these other big telescopes that are going to come online, right? I showed you the 30-meter telescope, the ELT, Earth-based telescopes, and they might be able at some point to study these systems as well and start to also return meaningful data. And it's this comparison of data from different instruments that are actually going to validate or not any life detection. That's most likely what's going to happen. Yeah. But you're right. so many have been bitten. But this story is just too good to be, to be kept about yourself.
Yeah.
You're gonna say, you know what scientists do, right? They do hedging. They write. They say, we suggest and we suppose that there may be, right?
Earth-like.
Exactly. So they may be given the, in certain situations, circumstances, and then of course you pass that to the media. What do they say? We found the life. It's always like that, right?
Yeah.
So, yeah. Another question. Did you have a question in the back?
Oh, at the L2 point, is it perpetually eclipsed from the sun by Earth?
No. Actually, it's not. The sun is too small to give a shadow, sort of. Sorry, the Earth. What did I say?
The sun.
Oh, sorry. No. Yeah, the Earth is too small to actually shadow JWST, and actually JWST is not actually at a certain spot at L2. It's actually going in an ellipse around it, so it's never really going to be in the shadow of Earth, which is why you have these huge, solar shields.
Because it is actually solar powered. The spacecraft is solar powered, isn't it? So
There's a small solar power. Yes. Well, there's two. There's a fuel that's used to target the telescope, as you mentioned. That fuel is expected to last 20 years, but there's a small solar panel
which
there
runs the instruments, yeah.
too. Yes.
Has it reached its farthest target? What telescope?
You mean, has it reached L2?
Yeah.
Yes. It's at L2. It was there. It reached there 4 months ago now, 3-4 months ago, something like that. And it's been in the commissioning. Therefore, they've been trying to, start all the instruments, make sure they're working properly, calibrating everything. So that's been happening for the last few months. And you can see that online. You can see the different steps of what they've been going through as they've been calibrating these instruments. And that's why I'm saying it's great that we have this talk now, because this is the end. This, end of May, beginning of June is the end of the commissioning. They're going to be starting to look at these things. These exoplanets, I told these 5 exoplanets, they're probably looking at it now, because that's sort of part of the end of the commissioning, the beginning, the some dry runs. They want to make sure that everything's fine before we start. So, it's fantastic.
They could have already found ET. Yeah.
They're already deciding how they're going to break news to us.
They'll never cope with this.
Yeah.
Any other questions?
Anything from Jenny, have you got?
Yeah, so I was just going to say, if you were going to bet on it, which planet or moon, exoplanet or moon, do you think would be most likely to harbour some kind of life form?
Well, if it's exoplanets, TRAPPIST, we have 3 habitable, rocky, terrestrial-like planets orbiting a dwarf, a red dwarf. I think, if we have a chance, it's probably one of those. And in terms of our own solar system, I think, Enceladus and Europa, if we're going to be finding life, it's probably going to be there within the plumes of water that are venting out into space. JWST is going to do some observations on these moons, but it's not going to be designed or characterized to really be able to find life there. We're going to have to send some spacecraft to actually go into those plumes. But when it comes to JWST and the exoplanets and the atmosphere study, yeah, these TRAPPIST systems, for me, seems like a great bet.
Thank you.
Yeah.
Thanks, Jenny. Okay. Well, thank you, everyone. Thank you for attending. Thank you very much, Bernard.
Oh, thank you. Thank you for having me.